Hello, everyone. Good morning. Thanks for the invite, Erica. I'm very glad to be here again. This is actually very kind of emotional to me because the last time I was here, it's when a lot of things that come up in the last year started, including with the support of the MI and working with you. And the results I'm sharing here today is kind of a mirror to what was shown last year or 2 years ago, actually, I don't know, in terms of applications of machine learning for weather predictions within urban areas. So, well, Erica already presented me. My background is actually architecture and urban planning. But in the last decade or so, I've been devoting my life to urban climate and how to use Earth observation, geospatial data science to improve weather forecasts and climate scenarios within urban areas as a function of land use, land cover, and the urban design and infrastructures at the mesoscale. And by mesoscale, I mean the metric scale, not in terms of 1 meter, 5 meter, but I'm talking about pixel sizes between 100 and 200 meters. The reason for this is that this is the scale in which architects and urban planners design cities. So whenever we do urban planning regulation, being at the city or the metropolitan area levels, we have to usually design the regulations and the ability to build and the green parks, the green infrastructure, the main roadways, etc., as a function of the natural and the artificial characteristics of the territory. And so this is like, for me, the sweet spot in terms of what's missing in terms of applications for urban climate, because in terms of microclimate, we already have very good models, physical models that employ advanced techniques to, say, estimate the heat exposure within a neighborhood at the metric scale or submetric scale. And this can be done for large developments and special projects within the city, but it's done at the site construction or at least a neighborhood. What's missing there is when you have to model a full city or a metropolitan area in an efficient manner. So the purpose of the research that I'm going to show is related to these kind of constraints. So being low cost, being scalable, and tackle this scale in between what's the regional weather, like the background weather, and what's the microclimate within the city. So we are trying to bridge these two, let's say, scales. Today, I'm going to present the CLIM4cities project. The CLIM4cities project is an ESA-funded project in the scope of the Trustworthy AI application. It's a 12-month project, so quite short, quite speedy. It's led by the MI here with us, and the consortium just says, okay. In terms of objectives, the objective of this project is basically to replicate things that we have been doing elsewhere, but also advance it in terms of the machine learning architecture. And the goal is to develop weather and climate models focused on air temperature and land surface temperature at the same time in larger urban areas, specifically in Denmark. So we chose 4 cities to employ this. Also, we want to provide alternative, innovative data sources for this. And for this purpose, we have all of our pipeline based on crowdsourced data, along with open data. That's the low-cost aspect of it. And then we want to foster Earth observation and geospatial data in general uptake for a more applied, let's say, decision-making process, namely climate adaptation. And this is more related to the climate scale or temporal scale of the application. So having said this, so the drivers are basically something that is quite well established, I would say, in terms of the community. So we know we have the climate change prospects for Europe, which are not looking that good in terms of exposure to heat-related hazards. In some cities, I wouldn't say, maybe that's not the case of DMI, but Denmark, but in Portuguese, definitely it is. We have energy poverty issues because the houses are not acclimatized and they do not have air conditioning. So a lot of people suffer from thermal discomfort and all the health issues that come with it, along with energy consumption if air conditioning has to be installed. And we also have an issue with aging population. I would add to this more recent driver about migration, because we are starting to see a lot of fluxes of people coming from different locations which are not yet acclimatized to local weather. And when all of these things come together, so climate change, the previous acclimatization of people coming into Europe, the energy poverty issue, and so on and so forth, it's like a melting pot of issues that drives the need to have more applied solutions of this kind of scientific expertise in terms of urban climate applications and urban weather, let's say, prediction. So we wanted to develop something that is efficient in terms of computation, reliable. So one of our basic constraints is that we have to improve the resolution while keeping or improving the precision. So this is kind of our metrics for evaluation. And we want also to translate this kind of layers into meaningful decision-making process. So of course, we are talking about air temperature, like I said before, also land surface temperature, and I will talk a bit later about this. But in terms of what the air temperature is concerned, which is basically what we feel and what drives our exposure the most, we are not only concerned about the air temperature prediction, but also its translation to certain indices that are relevant either for the energy or for the healthcare sectors. So we are building a model that targets the extremes. And this is kind of a differentiating aspect, because models tend to the mean, being physical or machine learning driven, regardless of that, they tend to the mean. So using the crowdsourced data and observations and some data augmentation techniques, we are able to improve the model's predictions on the extremes, which is basically our target, especially the heat extremes, which tend to be underestimated by available models, especially at the regional level. So this may be familiar to some of you. This is what was presented last year or so. So this is the machine learning model that is now operational in Lisbon. It downscales or upsamples the weather forecasts from the National Weather Services here in Portugal from about 2.5 kilometers to about 200-meter pixel size. This is a sneak peek in the city center of Lisbon, just to depict which areas are cooler and which areas are warmer. And for those that might be familiar with Lisbon, might not be the case of everyone, but the patches you see in blue in the lower print actually resemble areas that are either green infrastructures or subject to the ocean breezes, like you see here on the left-hand side. And this was done in conjunction with the local municipalities. It's targeting them. It's still, I would say, a scientific effort and not a service-like application yet, even though it's operational, and we are right now evaluating on the fly the performance. It uses our own model predictions and, let's say, the background. So now we travel to Denmark, right? And the idea is to predict, replicate this model in Denmark, having 4 cities as the target. Not all of the cities will serve for training, and our goal is to basically see if our approach is scalable or not, and what's the relative cost of each city compared to the previous one. And when I say cost, I'm not talking solely about money. Of course, everything can be summed up to money, but I'm talking mostly about effort in time, effort in computation, and also the feasibility. So how feasible it is to scale this kind of approach to other locations. Moving forward, so the rationale for the model is basically built on Lowry's equation. It's a very old equation, I don't know, from 1920s or so. And basically, it states that every local weather parameter is a function of the background conditions, and then the factors that are natural, like landscape, and the urban. So for him, the equation that sums up what the urban climate or the urban weather is the sum up of all of these things. In some aspects, there are things that can cool down the city. Other aspects can warm it up. To serve just as an example, In terms of topography, it's completely different to be on the hilltop than being on the valley, and it's completely different to be on a slope that is exposed to the prevailing winds or one that is sheltered from them. All of these aspects contribute to warming or cooling the city, as well as the density, the shape of the buildings, the urban canyons. And even though we are targeting an 100 to 100 metric scale in terms of pixel size, all of the summaries of these aspects have to be taken into account when we look at the background synoptic conditions. So this is basically the rationale that is put forth. And in terms of the response variable, we are using citizen observations. Mostly these come from Netatmo, but the MI also has a good array of data from the lone box stations. And we are employing a data-driven modeling approach. So this is a downscaling method. It's not a prediction in the temporal aspect of it. It's more like a special prediction in a sense. And the proof of concept of the application basically is to downscale the weather and then kind of replicate these to climate projections because it's scalable to that purpose. So the response variables are twofold. We have on one side the air temperature that I've been talking the most about, and now we are adding the land surface temperature. Why are we adding the land surface temperature? The fact is that land surface temperature, because of the high resolution and mid-resolution satellite missions, is a good proxy for validation. And we know for a fact that the air temperature and the land surface temperature correlate, even though not in time, but in space. So during the night, the land surface temperature tends to show the signal of the urban heat island effect, and that's where it correlates the most with the air temperature, because the stored heat flux during the day is released back to the atmosphere, and this is the moment in which both things align. And in this aspect, land surface temperature serves as a good proxy for urban climate applications and spatial planning, especially, I would say, on the climate scale, while the air temperature has the double fold of the climate and the weather scale as well. This was actually talked about by Alte in the previous climate coffee in the terms of the needs of the users, because they clearly state that for, let's say, long-term decision-making, land surface temperature is useful, kind of a seasonal maps, typical maps, and air temperature is useful more related to human health aspects on the short term, so weather forecasts and alarms. So in terms of the more machine learning aspect, so if we want really to test if the model is scalable, one of the things we have to see is whether we can train a couple of cities and just predict another one and see how it comes up. So to this effect, we decided to have a machine learning data set that shall be published in the end of the project, comprising 3 cities and have one left out. We are also conducting a split in terms of temporal scope, and we learned from the Lisbon experience that the temporal scope has to comply with the temporal time series splitting methods because of the autocorrelation of the time series. So we cannot just randomly sample, we have to keep them together. And after some back and forth on this and having consulted with the literature, the best results are achieved when we basically take out 1 week out of each 4, because there is kind of, it might have a drift in terms of climate change, of the warming, etc. So leaving just 1 year out is suboptimal, because you may not see things that just happen in that year from the time series. When we leave 1 week out, it's much easier because you can comply with the temporal autocorrelation of the structure in the 3 weeks of the month and just have 1 to validate. But there are other aspects to this because we want to test the model performance on heat and cold waves. So we have to comply with certain criteria to make sure that heat and cold waves are adequately sampled both in the training data set, the validation data set, and the test data set. Also, just a couple of words on lexicon. So even though for scientists, we usually tend to use validation as the final unbiased validation, for the purpose of this today presentation, I will refer to that as test. just to comply more with the machine learning lexicon. So test is like the final unbiased validation. And when I say validation or fine-tuning, it's the intermediate step in which you adjust the model while still training back and forth. Okay. So this means that our split is actually quite complex in this sense, but it's like scientifically informed. It's not like random. And we have the first step, the special split. So we have three cities, 2 cities for training. Actually, it's 2.5. This is original plot from the proposal. We since decided to revise this. We have 2.5 cities split for training and testing, and validation, and then we keep 1 city just for prediction and final unbiased validation / testing. We have 4 years of data that we collected, and for this we train with 3 years and we leave 1 year out. So from those cities that were used for training and for fine-tuning, a year is left out, and the other city is left out completely, both in space and in time. Then we have the data split also in terms of unused data sources. And to this effect, we are seeking data sets that are available online to cross-check it. The validation of the model, this has not been done yet. This shall be done in the end with the final model. We are still into machine learning training. And then we have also the weather condition split. So we have normal weather, which fits for us between the 10 and the 90th percentile. And then we have the extremes, and we use the 10th and the 90th percentile just to comply with what's usually out there in terms of relative-based indices. And these extremes are left out both for the training, the fine-tuning, and the final unbiased validation / test, just because we need to ensure that all of these 3 splits have the same statistical distribution. Some data augmentation techniques were also put in place to replicate these extreme days to make sure that we have enough of a sample in the training data, not to have it overfitted to the mean conditions. Also, if you have any questions so far, please feel free to interrupt me. We can discuss it while presenting. Now, in terms of the results I'm going to show, this is, of course, still into development. The project hasn't finished yet, but these are preliminary results that I think are quite interesting. And so the response variable, as said before, is air temperature observation and LST data. For the air temperature data, we have NetAtmo data comprising about 2,394 NetAtmo stations just for the Copenhagen city. Metropolitan region, actually, or functional urban area, which is the main city and all the locations that are dependent from the main city in terms of the metropolitan flow of people and also other dependencies in terms of services. And then we have this is actually, I think this is wrong. I didn't update this because this is about the stations that it's the other way around. It's the ones that have less than 30% or so in terms of quality controlled. So most of the stations pass the quality control routine that we implemented. We are employing the method from Met Norway, developed by them, with some tweaks. We did some tweaks to the workflow, but it's published there, so it's kind of a statistical quality control method. And what we found compared to Lisbon is that there is many more stations, and the ratio of approved stations is much greater compared to Lisbon, which is cool to see, and it helps out the training a lot. In terms of the LST data, we use Sentinel-3 images available, but also Landsat, and we are pairing them. There is like a big problem in Denmark because the cloud cover is a lot. And we coming from Lisbon are not used to that kind of statistics, but indeed we don't have that many scenes available. But still, because users are not concerned in the weather scale or by image prediction, what they want is like typical maps. It ceases to be that worrisome because we can compute summaries, and it seems that it's actually what the users prefer. So in that sense, well, it's a constraint that shall not have large implications. The Predictors are many. I'm just showing here some of them. So you see the response variable of the air temperature in the upper left-hand side. Then we have, of course, the digital elevation model, but this is post-processed to certain topographic-based indices like topographic exposure per wind direction. We have also the distance to the coastline. We have urban density, imperviousness, local climate zones. These local climate zones are algorithm that we develop that is specific to us. It's not the local climate zones available elsewhere. It has much greater detail. And also, of course, tree cover density. There are more predictors, but all of them look like this in terms of their resolution. So things between 10 and 100 meters of pixel size resolution originally that we resampled to 100 to 200. Some overview of the response variables. So these are some plots from some stations in Copenhagen. In the upper side, you can see the WMO stations to see how the model that is existing, and it's DANDRA, it's reanalysis from DMI on this domain, which has a very accurate prediction of the weather, the air temperature, and the weather scale. But still you can see kind of a pattern of noisy predictions in the summer. This actually quite agrees with the AROM model implemented in the Iberian Peninsula, which tends also to have a larger deviation during the summer and actually to underestimate the extreme heat, special in the urban areas in which the urban heat island actually adds to this, and especially during the night, which is when the urban heat island effect is more prominent compared to the background. In the below plot, you can see the percentiles and the distribution of the net atmos stations, and you can have a look of how the 10 and the 90th percentile follow the distribution. In this case, it's not the 10 and the 90th percentile for the day of the year, it's of the observations themselves, because these are the percentiles that we kind of use for the quality control. So we leave out observations that fall outside. Not exactly this, because we use the interquartilic range and we differentiate in the warm and the cold extremes. Extremes, the limits, because the net atmos stations have a slight warm bias in 1 degree Celsius approximately. So it's differentiating, but still it's useful to plot it out just to see the, let's say, the distribution of the values over the Copenhagen region. So starting to train, this is what it looks like in terms of the availability of stations. For those that might have seen the similar plot done in Lisbon, we can see that we have many more stations and many more stations with 90% of OK quality control observations. I mean, on the full-time series used for training. You can also see that they are quite dense within the Copenhagen city center and its main outskirts. So this is good because it allows us to have a grasp on the spatial patterns as a function of the predictors that I've shown before. Now, moving ahead to some preliminary results. So this is what DANDRA looks like. This is a specific warm day in Denmark in 2022, in which temperatures rose up to 30 degrees. And this was a warm day, so it's from the sample of days that are classified as heatwave days, kind of. So the resolution of DANDRA here is resampled to approximately 0.04 degrees. The grid is not in orthogonal to this projection, so this is why it was resampled, but this is very close to the native resolution of the reanalysis. And having looked at this, in addition to the pixel size in proportion to what we see as the location, you can see, looking at the city, that you don't see the real patterns of the prevalence of the city. So the green parts, the areas that have dense neighborhoods, etc. Now, these are some preliminary results of our model for the same day. And here you can start to see real patterns, both at the mesoscale and the urban scale, let's say. And you can see, for instance, some pixels that are cooler around here. And you can also see this patch here. This is related to areas of the city which are not as dense compared to others. And you clearly see, especially during the night now, this, well, it went away. Especially during the night, even though the absolute temperatures are lower, you can see the pattern of the city within the differentiating temperature compared to the background, which is what we expect to see according to what we know about the urban entirety effect and its temporal evolution during the night. This is promising results for us in the sense that in terms of spatial pattern, which is when we are always worried that the model can hallucinate of sorts, it doesn't. This one I'm showing is a random forest, but we are actually training several models and intercomparing. This is just not the best one because we are still training and we achieve best results more recently, but it's like the previous to last. So the one that we produced the predictions last. Here's some specs of the model results. So in Lisbon, for reference, our own model is closer to 2 degrees Celsius in mean absolute error. For comparison here, in Denmark, the DANRA is more closer to 1 degree Celsius, which is actually the target precision according to the ECV frameworks of WMO. And we are able to reduce the error to below 1 degree Celsius. Now, this might not look like a very strong reduction on the average, but the fact is that in certain extremes, this is important, especially in the city center, and especially during the night when the urban entirety is greater. And while we are still validating during heat waves and in certain locations, because this is still a work in progress, from our experience in Lisbon, sometimes we can improve the prediction during heat waves in the city center by 2 degrees or more. Compared to what's predicted by the AROM background model. And we hope this is the same here. And we actually, when we see the statistical distribution of the error, we can see that our model adjusts the distribution to have the mean on the 0 in terms of the relative error, which is what's desirable. So we are able to correct kind of the cool bias of the DANRA model in the city, which is what we actually aim for. Now, in terms of next steps, as said before, we are still into validation. So we are still training back and forth the model, fine-tuning, compare different architectures, neural networks, random forests, also some linear models for reference. Then we have to test against unbiased data to see what's like the ultimate validation. And this is what I said before about leaving one city out and validate it with WMO stations, so stations that are unseen whatsoever by the training because we don't use them. And also compare with other data, other models, and other, let's say, special data that is available on the urban entirety effect to benchmark the results. In terms of applications, we also have a WP work package that is going to start next as soon as we have the model more complete, which is to shift the land use land cover and shift the input air temperature to replicate what could be future climate scenarios. And in this sense, we are fetching SMIP-like predictions, not predictions, but outlooks, scenarios, projections, sorry, the word was missing. And also, like we did in Lisbon, having the possibility to tweak some land use land cover pixels to see what's the outcome in terms of the response of the model, like a sensitivity analysis of which patches of the city can become warmer or cooler as a function of developing new green infrastructures. And well, this is work to be done in the next month, and we hope to present them like in the first half of 2025. Well, and with this, I conclude my presentation. Please follow us, check our publications on Zenodo as well and on LinkedIn. And with this, I conclude my presentation, and I'm happy to respond to any questions you might have.